thank you everybody for joining me on this session. I know it's unusual to see a PostgreSQL session on an SQL Server conference, but we are here every year so far, and we will try to do that every time. Okay, so today I'm going to be talking about extendable by design. So what is PostgreSQL, how is it extendable, and how to build generative AI applications with it using vector storage and Azure AI. Please remember to evaluate the session. That's very important for me and for the event organizers, so I appreciate the time you take. The slide will be repeated at the end, so you will be able to also follow the link. So the agenda for today is what is PostgreSQL, and we will spend just a bit of time on that. How is it extendable? What do I mean by that? And we will go through building an email helper. So we will go through basic search, then extending it with full text search, then doing an AI-enabled semantic search, and finally doing some playing with RAG, which is retrieval augmented generation. And I will go over some of these topics as we move through the slides. So what is PostgreSQL? PostgreSQL is an open source database originating somewhere in the 1980s. It's a successor to Ingress. A lot of its history was covered by Silvano, my colleague, yesterday or a day before, I think, on one of these 100-minute sessions. So if that's recorded, go and watch it. But what you need to know is that this database has been created to explore what can be done, what methods of storage can be done. It even didn't start out using SQL as the language of data retrieval. It used prequel, and it's very pluggable and changeable. You can change indexing methods, add data types. You can mend it and bend it towards anything you want. So it's very quick to add new features as they appear on the market without changing the core engine of the database. So for example, you have functionality like JSON storage, geospatial constraints, ACID compliance, rich data types, full text search, indexing, and so on. And on Azure, we build around PostgreSQL, providing some of the typical operational ease of performance insights, security, and things around that. So what is extendable by design? Through the years, as PostgreSQL was developed in the open, a bunch of interesting extensions that really opened up a whole field of new features were developed. One of them is, for example, PostGIS, enabling geospatial queries and data storage, JSON and JSONB. JSONB is for binary representation of the JSON, which is storing, retrieval, and operation on JSON data types, including indexing. So you can index JSON data types, and you can do path queries over JSON fields. So you can have a where query that digs deep into a structured JSON file to only find rows that contain a JSON document with specific value in a specific field, including dictionaries and arrays for lookup. There are special indexing types like GIN and RAM, and these are like inverted indexes for full text search. They are also used for JSON indexing and several, and recently for vector indexing. There's also this extension called pgvector. It's easier to remember that it's for trigraphs. It allows some interesting things that we'll go over in a moment. There's full text search Citus and a bunch of extensions that we develop at Microsoft to integrate with our services like Azure Storage and Azure AI, but also new on the edge of development extensions by the community like pgvector for vector storage and working with embeddings. So going through some of the examples, here's a query showing how you can create a table with all the roads within the city of Prince George. That demonstrates the type of queries that you may be doing if you are enabling the PostGIS extension on your database. This is how pgvector works. So that's my favorite show of feature. You might have done this in different databases. You can see this like query with an unanchored wildcard search. So there's no way to use a normal index to look through the database. Essentially, there's no way to speed this up if it's a wildcard search. In PostgreSQL, thanks to the tree graph extension, you can actually build an index that will be able to be used in such wildcard searches. And in the second example, we can see a regular expression query that is supported with this special operator in PostgreSQL. And using this extension, the index is built with it can also leverage the index when you are doing regular expression searches over the database. So you can imagine there's a lot of use cases where a regex search being sped up by an index is a very nice thing to have. If we are going about third-party integrations, it's very nice to be able to, for example, directly from your database, list all the files in this Azure storage, blob storage account, and list the files in the demo container. And as you can see, I have a bunch of files here, but extensions can integrate very deeply into PostgreSQL. So for example, with the Azure blob storage extension, we decided to hook into the copy command, which allows us to teach the copy command what a blob storage URL looks like. So you can copy directly by providing a file path to a blob storage URL, tell it that, hey, this is in CSV format, has a header, so skip the first line, and just load it into my table. And that's, of course, done between two backend services on Azure, so the networking link is very good and likely better than if you would be uploading the same data. And the integrations can go even further. At Microsoft, we develop a fully open source extension called Citus, which enables row-based sharding and schema-based sharding for the PostgreSQL database. So you can have the same data set across multiple nodes in various sharding methods, essentially enabling horizontal unlimited growth of your data set. But we are not going to talk about all of these things. We are going to try and build a mailing list helper. So the PostgreSQL project, being very old itself, has a grounded community in methods of development, how they were done in the past, right? So a lot of the things are happening on the mailing list. So if you have a question and you want to learn something about PostgreSQL, or maybe you want to change the database, what you would do normally is you go to the mailing list, ask your question, or search for the mailing list, because likely in the 30 years or so since the project started, somebody asked that question, and there's likely a much better answer in the mailing list than on a random internet page that you might find on a search engine. Let's start with basic search. Over a few days, I did write a sample Rails application that loads the data, and we can go over to it if we end up having some time. But for now, know that we have this emails table that has roughly emails loaded from 1998 and right now from 2024 March, and we can load more live if we want to. And you can imagine how you would build a search application where you allow the user to enter a search query like write ahead log, and you could do these like searches for the content to find write ahead log. And that would hit something because it's likely that somebody used that exact term. But if you try to do something like wall logs, then it's less likely that somebody used this specific combination of words in that sequence with just a single space between them. So that's not useful for retrieving sensible information for what the user might have wanted to learn. And same if you have even simple variations like 2 spaces instead of 1 space. Well, you can of course add the wildcard search everywhere, but you get the idea. Small changes in how things are worded or placed between one another means that you will miss content that somebody was searching for. And again, sorry, that's the example with the added wildcard search. So The next thing you would do is you can reach out to some of the features that PostgreSQL has. And in that case, that's full text search, which is a built-in vector storage data type with functionality to do tokenizing, stemming of documents based on, you can write your own tokenizers, ranking features, etc. And you can add weights to the content, so you can actually build full text search documents as you would do in Elasticsearch, for example. But the added benefit is running an Elasticsearch cluster is a new undertaking. That's something you have to learn, you have to deploy, you have to manage, and you have to ETL data between one service and another, which adds latency, time, operational costs. So PG might get you 80% there, and that's enough, or it can get you full way there, depending on your requirements. So in this example, we are adding a column TS of the data type TS vector, generated always as, and we are going to build a document by concatenating the subject and content, and I am the subject and content, and I'm adding weights to this content. So I can say that something is the most important A and the least important D. So that way I can decide that matches in the subject are more important than matches in the content. But maybe I would like to parse data that's referenced in the email. For example, somebody links to a web page. You can actually, in your application code, go to that web page, tokenize that web page, and store that as weight C. And that way you are not storing the external web page at all, but you can still hit it in searches, and the email will be brought back in the recall, even though it doesn't have a single word from that specific article. But that way your users get a very matching and relevant search experience. So this is how we build this column. And what this means that for existing data, the tokenization will not happen immediately. Well, it takes time, so not immediately, but it will transactionally build the tokenization and add it as a column. And for every new row that we insert, we automatically get that, even if the code that adds the row doesn't know about its existence, right? So how does this vectorization look like? So here's an email that has been tokenized, and this is the TS column that we just added. And you see a bunch of words, or something that looks like words. These are stemmed words that have encoded their weights and positions in the document. So you can see this kappa BL is likely the word capability, or any forms of that word, like capabilities, capability, or other permutations of case-sensitive spelling and things like that. And their positions, so 3A is third token in the title, and 182B would be 182nd token in the content of the email with the weight B, right? This is the example where we can see the word log was encoded as 15B, 35B, and we can see where that is in the document. That's the word logging and the word log. And I know it's not easy to map it, like, is it 15? It's not. So I'm going to show exactly how that works. There's this, and PG is nice and transparent with everything. Like, this developed by engineers in open source, so you get all the guts exposed to you. So you can call this tsdebug command, providing it the email data. I just briefed it out for to not make this slide even less readable. And essentially, I'm skipping everything except the blank words that get thrown out here, and I added row number over to have the count of which token is it. So if we go down, you can see the 15th token is the ASCII word logging that goes down to the lexeme log. So this is how it works essentially. And of course, there are helper functions, so you don't have to do that. Okay, how do I later use that in my document? There's this TS headline feature that you can call over the document, and I'm shortening stuff for brevity again, with the same query as the user provided. And you tell it to highlight all examples, and what you will get is in your query, it will return the text with the word highlighted with the bold HTML statement, and you can select what type of token markers it will insert around the matches. And you can also tell it how much context and around the document it returns. So for example, that way you could do the thing that you see on the search engine where you type something and you see an excerpt from the website with a few keywords highlighted. So that's how you would do that very quickly with PG. So how do you search? How do you do full text search? So this query is larger than it needs to be because I also want to show you the ranking that's used to determine what's relevant and how far. So I'm adding this TS rank, which is this is a built-in ranking function. You can write your own. With this special web search to TS query with the English language right ahead logging. The web search to TS query allows you to do things like you would on search engines, which is give me salt and banana but without avocado, so like and or with the same syntax as you would on a search engine. So taking things into brackets, using a minus sign, writing and or and things like that get translated into a special language that's used as the query input for this TS vector data type. So later on, this is the search operator that does the full text search. Like I said, you can implement your own methods in PostgreSQL. This one does full text search, ordered by rank, descending, and we can see the rank, which is a number from 0 to 1. And here you have like a pretty good match and just one match in this sample set data that I have. But you can also see that this did a sequential scan on all the emails. So that's a full table scan. So that's not good. So what you can do is you can do indexing. And I hope this is big enough, okay. And with indexing, you can, okay, this is another example with a full page scan. I didn't add an index here, but we have an index being created here using gen on the TS column. And after the index is created, if you repeat the query above, which has explain, analyze, which is how you see query plans executed in PostgreSQL, and you can see that it does a bitmap index scan on this index that we created, reducing the time to less than 1 millisecond from 3 milliseconds. So what is pgvector? So we talked about full text search, and you can imagine like if we are building a mailing list search, that's already very helpful in getting better results. But how do we go from here to something better like semantic search, where I can type things like give me emails that talk about recipes with avocados, and it knows to include things that contain guacamole because guacamole is made out of avocados, right? So to get that type of knowledge insight, we need to have vector storage. And pgvector is a popular open source extension that adds the capability to store vectors, but also to do operations on vectors like inner product, cosine distance, L2, and etc. And also, you can do indexing over vectors stored within pgvector. And there are two types of indexes that are available for this, which is IVF inverted file index. And if you want to think how IVF works is you need to have some data already in the table. There's a pre-training step where it goes over the data and does key means clustering. Essentially, it splits your data set into multiple lists, and you can control how many lists you have. And within all of these lists, it has the center of a cluster and gets a bunch of entries that are around that cluster. So later when you are searching for your data, you are deciding how many lists you are probing. And if you tell it to go through all the lists, then that's the same as doing a full scan over a table. So essentially you are fine-tuning how many lists do I want to visit, and that impacts your recall speed and accuracy. So you are making trade-offs with how much data you are finding. And the benefit, of course, for IFV is the index is fast to build and memory efficient. You can tune it very nicely, but has worse speed of recall trade-off. The HNSW, hierarchical navigable small worlds, which is a mouthful to spell out, is a way to do a graph-based indexing method. And a nice way to understand it is it works in layers where you have the top layer that goes into a smaller layer that has more local points and down to the smallest layer. And you can think of it as you would with a city, for example, where you have the highways leading to specific areas, then you have some local roads, speedways that lead to certain areas of the city, and then you have the local roads and the smallest roads, right? So that way you can quickly get from point A to point B by knowing roughly where you want to go and which highways to go through. And the benefits of HNSW is, well, the trade-offs are it takes longer to build, it takes more memory, it has better speed of recall because it's traversing a graph instead of doing an extensive search through many lists. And there is no training step, so it can be created on an empty table. With the previous method, you have to have some data so you can build these clusters around your data. Okay. So what is Azure AI? To get to use vectors, we need to have embeddings. Azure AI is an extension that we developed for PostgreSQL that allows PG to directly use various Azure AI-related services. That includes cognitive services and OpenAI APIs. So you can, from cognitive services, you can do fun things like detecting the language somebody is using in a document or doing live translations. And you can do that in a query. You can grab the email, check the language of the end user, and present the translated email as if it was in their own native language. And that's all from within your database without adding it to your application code. But you can also do embeddings. So calling create embedding, providing a deployment and telling it, hey, you have this email, give me an embedding for it so that you can later store it and search it. So what do we need those embeddings for? For RAG. And RAG is retrieval augmented generation, which is doing all of that AI stuff is costly. Vectorizing all the data, then you have to throw all the data into a model to have that model output some information. If you go to ChatGPT and start asking like PG questions, PostgreSQL questions, it will give you decent answers, but these answers may be outdated, maybe they are from 30 years ago, or commonly repeated patterns that people still believe are accurate, but they stopped being accurate a few years back. So how do you improve that? And also reduce the cost of using these big models, because I don't want to feed the whole mailing list into a large language model every time somebody asks a question. So what you can do is you can find the relevant email threads that somebody is talking about the thing your user is asking about. Then you can grab those emails, add them to the prompt, and tell the machine learning model, the large language model, to answer the question based on the information you provided. And that way the information is grounded in the data set instead of being sourced from whatever the whole data set is that may be irrelevant. And for example, you may get answers that are based on something that was read about SQL Server that a large language model doesn't make the connection that this doesn't apply to PostgreSQL. So I think I got the slide wrong, but this is a sample prompt that you could use, for example. So you would have a placeholder for the document and some text like answer the user's question using the document above. Keep your answer grounded in the facts of the document. If the document doesn't contain the facts to answer the question, return, have you tried turning it off and on again? And I outed myself as liking the IT crowd. So what is the write-ahead log in PostgreSQL? And here is an example that we can go over in Azure AI Studio if we get some time left before I go through the slides. So how that would work is you would provide the document, that's a snippet of an email, ask the model, and the model should be able to answer based on the data that you provided. So it should read that, okay, the write-ahead log is more conventional way of assuring atomicity instead of trying to search the internet for what that is. Okay, so now that we have all the concepts out, we can get to actually doing stuff with vectors. So we create the vector extension, the Azure AI extension. We configure the endpoint, providing some secret key that we have from the service. We provide the subscription key. And we do the same thing as we did with full text search. This is a new thing, but you can see the parallels that you can extend PG without touching the engine in similar ways as it has been over the years. This is a new thing, that was an old thing. And if there's another new thing, you can expect PG to adopt it similarly. So we can see that we are adding a column email embedding with the vector of the size 1536, which is the exact size of the embedding dimensions that OpenAI returns. Generated always as a call to OpenAI create embeddings using the text embedding ADA002 model. And this here is a substring limiting the concatenated data to roughly 8K characters, because that's the limit that this specific deployment takes. So I'm playing safe here. I know that some subjects are nil in my data set. Exploring data sets from old emails is very fun. They are unexpectable. So we are going to concatenate the subject of the email and concatenate the content of the email. And this is casted to the vector and stored. So this is how you search for it. We have this new operator on the added vector data type. This does the inner product. So you can search through all the emails ordered by this relevance score, because it will return a number like we saw in the TS rank for full text search. And we have to generate the embedding from the user's query. So the user in the website wrote, what is the write-ahead log? And we call the OpenAI, create embedding, we get the embedding, do the ranking over all the emails, and we get a bunch of messages. And you can see the titles: PostgreSQL capabilities, logging transactions, reading and writing at the same time, row level locking, PG log, automatic logging of every transaction, how to access. So these emails likely have something to do with write-ahead logging. And of course, you can do indexing, because again, we don't want to do a comparison over all the vectors. That's not a cheap operation to do. So what you can do is so this is the query without the index. So you can see it did a full sequential scan over the emails. Then it does the sorting, typical stuff in limit, because I limited the result to 5 rows. But if you create the index, okay, big enough, on emails using HNSW, which is the second indexing method, for inner product, you can see that the result of the same query is an index scan using email embedding inner product index that we just created on emails. And you can see the query execution time went to less than 1 millisecond from over 10 milliseconds. Like the data set is not super huge, But the bigger the data set, the bigger the difference is. And we can take a look at some email, one of the emails that it finds. So I asked it a different question. What is the page size? And I used another Azure Cognitive function, summarize abstractive, because the email would be too big to fit on the slide. So we asked it to essentially summarize it for us, and it said the document contains a series of questions from individuals seeking advice on how to store large amount of data, blah, blah. And specifically, the 8 kilobyte page size of PostgreSQL and the 8 kilobyte record size of tuple size in PostgreSQL. So we know that it found something that talked about the thing that they asked about. That's still not an answer if it will be able to tell me what I need to know, but that's a start. So here is a bigger query. It just has, so most of this query is something that you all seen before. Emails have replies, replies may have replies, so that's a recursive CTE listing a mailing list thread, but we added this search, so we may search for what is the page size, and we get 2,000 characters of response that we can feed to an ML machine learning model to make an answer from. So now that we still have some time left, we can play around with it and ask it some questions. So I'm going to exit my presentation, hopefully. Okay, it worked. And what I'm going to do is, for the sake of time, we will open Azure OpenAI Studio, go to the Bring Your Own Data playground. And this is on my phone connection, so sorry for any latency. We are not going to do any data sources, but we will be playing around with it. So this is the basic GPT-4 model. We will add the prompt that we saw in our sample. So this is the instructions. If you don't know the answer, don't answer, right? So what is the page size in PostgreSQL? Currently, this thing has no data in it. If I clicked apply, so it tells me have you tried turning it on and off again, because there's no data in the sample prompt, right? If we provided the example that you saw in one of the slides where I had the snippet of an email, so I'm replacing the prompt, hitting save. So what it did is it started a new chat session. I'm going to ask the same question. What is the page size? I don't need to tell in PostgreSQL because it should know from the document, and it failed completely. So that's, I guess, an unpredictable result. Oh, sorry, it failed because I provided the wrong content. So this one tells me what is the write ahead log. And it knows what the write ahead log is because that is in the document. So it tells me the write ahead log wall is a more convenient way of assuring atomicity in PostgreSQL. Before a transaction is written to the database, it is written to the transaction log, which can be replayed if necessary. So that was an answer based on the document. But it's nice that we saw that it fails to answer the page size because you get a feeling of how that works. And if you look at the code, this is how you would roughly do it in your application. So everything else, the vector embeddings you have present, what you need to do is you need to retrieve the prompt. So you would do the vector search in your application to find the relevant documents, concatenate them, and then provide them into an API call that does the completion on the provided prompt with the user question added to it. Okay, so if we go to some of the other prompt examples, so I have a bigger one here. Sorry, this one is without the prompt text, so I have to paste it, save. So this was generated with when to vacuum query. So PostgreSQL has this concept of vacuuming data because PostgreSQL is a copy on write database. So if I ask it, when should I vacuum? Hopefully it will answer my question. So it tells me that AutoVacuum should handle the vacuuming for me completely. And I shouldn't really need to vacuum myself. And I have a different answer yesterday, but it's to the same extent. It tells me that there are some cases that I need to vacuum manually, like with partition tables, that AutoAnalyze will only collect statistics on the partitions and not on the partition table itself. And after creating an index on an expression, you might want to do vacuuming manually. And additionally, AutoVacuum AutoAnalyze cannot process temporary tables, which are not accessible outside the owning session. Therefore, it's important for performance that these tables need to be handled manually. And that's based on, and another interesting example is that I previously did this query, and I think I have the query here, so it will be easier to see. I had this query when to vacuum without this date clause over 2020. So what happened is when I ran this with most of the emails coming from 1998, PostgreSQL didn't have AutoVacuum back then. So the answers I got from the model were not so good. And even after I added the data set from 2024, it still wasn't good because there was a lot of data indicating in the set that those 2024 emails are not that relevant. So it kept saying the wrong things. So I started filtering the date to be more relevant with the results. And that's important when you're doing these types of applications to do those hybrid search approaches. And that's why you may want to do full text search, filtering on specific columns, and then doing vector search. That way you are providing less data to the model and more relevant data to the model. The better you can get your source data cleaned up, the better responses you will get. And I think I had a bunch of a few more questions. What is the page size? So we can also open the what is the page size prompt, hopefully. And let's do the same thing. And sorry about that. I was lazy and didn't add it to the sample application code. I have it in a very bare bones manner right now. So I'm cheating by doing manual retrieval augmented generation based on this. Okay, so we have this loaded, and the question I had is, what is the page size? So what is the page size? And hopefully it should tell me that the page size in PostgreSQL is 8 kilobytes. Oh, exactly. So that's the correct answer for this specific question. Okay. Let me take a look if there's anything interesting that we can cover. We can explore a bit the data set, I guess. I can still show the a sample email. Emails limit 1. So the big thing here is, of course, the vector itself. Maybe let's do this. So we can see that every row has the TS vector, which is the stamped full text search of the document as we saw. And every word also has the embeddings created, so email embedding. Which is the very large vector data. As for the data set itself, we can pick whichever mailing list archive we want. So we can, for example, grab the data from January which will download it. If you do any queries where date is over 2024, and before 2024 02, we have no data. And what we are going to do is we are going to load this data set, and that's somewhere on mount C users me downloads pgSQL. That's the data set from January. Maybe let's do more or equal. Okay, nothing. And we can try to import it. So what this is doing is it reads the mbox message files. It does the full text search generation on every row insert, and it also does for every row being inserted, it does the call to OpenAI to generate the embeddings for the model. And my code here skips some multi-part emails and a bunch of emails that are just badly formatted to be ingested that way. And if we repeat this query, we can see that we have like 14 emails now, and we can look at a bunch of them. So let's look at the subject maybe, the TS vector and the email embedding, and let's limit it to one email to not have too much on the screen. And you can see that even the newly entered rows have both the text search tokenization performed and stored, but also the large email embedding from OpenAI itself. And the application code that actually does the saving, which is a Rails app, so it uses the mail model. It doesn't know anything about this specific column or how to handle vectorization. It doesn't call itself to the external service. And when I actually added the columns, the code wasn't changed to handle that in any way. So you can change your existing applications to get that. Okay. Yeah. The question is, how is the tokenizer output stored, the TS vector data type, and is it compressed in any way? So I would need to look at the implementation of this specific extension to of this specific data type, because this one is part of the PG core, to know if it has any special handling. I would assume not. Rows that are larger than rows that don't fit in the tuple size, and there's some heuristics in should this fit in the page and in the tuple size, they get treated into something called toast in PostgreSQL, and that's a method of off-page storage for PostgreSQL, and that off-page storage has an option to do compression, and it's usually enabled. So if it uses toast, and I assume it does, then the large values that are toastable, I assume, would be compressed unless you configured it differently, and I would assume they are not compressed otherwise. Though, that said, in some cases, extensions may end up doing their own compression or some form of optimization for storage, so I would need to look at the code to answer that fully. Yes? Sure. So to repeat the question, in the example I showed, I'm sending all my data to Azure OpenAI, which is a service run by Microsoft. And the question is, can I run this and use the vectorization without sending things out to an external service? We don't want to do that. The answer is yes. You can, of course, provide your own vectors. So you can enable pgvector, that's just vector storage. You can do your vectorization, for example, on OpenAI, Hugging Face, or whichever provider you choose, and do vectorization that way. We currently don't have APIs hooked to other services. If you wanted to do it within the database like it is right now, we do have inference, which is getting there, so you could do something of your own, potentially. Any more questions? Yes? Sure. The question is the best practice to store your vectorized data inside a relational database, in this case PostgreSQL? That's a good question. Thank you for it. In this case, yes, you can use a specific third-party, for example, product just to do vectorized database storage. But what you are paying for with that is, like with the example of Elasticsearch, you have to ETL your data in and out of your set. So if you can have that vectorization local to the source of your data, you're reducing the latency. So it's not like your data is stale the moment the user wants to search for it. It may not make a difference in a lot of the cases, but there are cases where that extra time it takes to get the data out is not acceptable, or you may be paying additional operational costs of, I have this another thing that I need to operate on. And also you're losing a lot of things that are very nice in relational databases that we tend to remind ourselves when we have to have third-party services involved, including our own third-party services, which is transactions, right? Asset compliance. So what happens if that third party, like if your transaction fails? Do you go and scrub the data from that third-party vectorized database? In this case, if you're within a transaction, it's rolled back. It didn't happen, right? Maybe you paid the cost of calling that function, but you didn't have to think about what do I do? Do I have to go somewhere else and roll back the data set? And I guess that's all. Thank you all.